When we talk about a combination of functions, arithmetic combinations can be addition, multiplication, subtraction, division. So f plus g of x literally means f of x plus g of x. F minus g of x is f of x minus g of x. Fg of x means f of x times g of x, and f divided by g of x means f of x divided by g of x, being sure that the denominator doesn't equal 0. So, given these two functions for f of x and g of x, let's look at each of those combinations. So for f plus g, I'm going to add f of x and g of x, and then simplify anything that I can. So the positive 2 and the negative 2 would drop each other out, and we'd have x squared plus 3x. If we had f minus g of x, we would take f of x minus g of x. Don't forget to distribute your negative to every term that comes after it. And so your 2 and 2 would combine this time to be 4. So we'd have negative x squared plus 3x plus 4. All right, if you multiply f of x times g of x, we're going to FOIL those. So if we FOIL that out, 3x times x squared is 3x cubed. 3x times negative 2 is negative 6x. 2 times x squared is 2x squared, and 2 times negative 2 is negative 4. Now, none of those are like terms, but I probably would write them in descending power order, x to the third, x to the second, x to the first, and then the constant term. And then f divided by g is just f of x divided by g of x. The only way I could simplify that, like I can't cancel these 2's here or cancel these x's. You can't cancel things that are being added or subtracted to something else. You can only cancel things that are being multiplied. So if I could take a greatest common factor out of the numerator and a greatest common factor out of the denominator, and they had something in common that would reduce, I could do that. So this is in lowest terms already. Now, we also can do combinations with values. So instead of f plus g of x, I can do f plus g of 2. So if f plus g of x literally means f of x plus g of x, then f plus g of 2 just wants me to put 2 in the place of x. So let's put 2 in the place of x, and let's put 2 in the place of x. So let's start with f of 2. What does f of 2 tell me to do? Well, it tells me to put 2 in the place of x in the f function. So we'll do 3 times 2 is 6, plus 2 is 8. And then g of 2, I'm going to put 2 in the place of x in the g function. So 2 squared is 4 minus 2 is 2, so 8 and 2 would give us 10. If you've already done the combination, as we had here, we had already done f plus g of x and gotten x squared plus 3x. If I already know what f of g of x equals, then if I want to find f plus g of 2, I can just put 2 in the place of x. So 2 in for x and 2 in for x, and you'll notice we get that same 10. So it doesn't matter which way that you do that. So combinations are very straightforward. If there's anything challenging about them, it's their domain. So to find the domain of the combination, you're going to find the domain of the first function and the domain of the second function and see where they intersect. They both have to exist in order for the combination to exist. So I find the domain of the two separate functions, see where they overlap, and that's going to be the domain of my combination. So let's look at f of x. F of x is a polynomial. Your domain is going to be all real numbers unless one of two things happens. You get 0 in the denominator, or you have a negative under a square root or a fourth root, an even indexed radical. I don't even have a denominator or a radical here, so that means that my domain is all real numbers. Similarly with x squared minus 2, no fraction, no radical, my domain is all real numbers. So if I'm looking for the intersection of the domain of f of x and the domain of g of x, all real numbers with all real numbers, that's going to be all real numbers. So that means that the domain of the addition and the subtraction and the multiplication are going to be all real numbers. But when you get to your division, you have another thing that you have to contend with. Remember that your denominator cannot be equal to 0. So even if your domain is all real numbers for all the other pieces, you always need to check your division to make sure that you don't have an additional exclusion there. All right, so our denominator cannot equal 0, so we're going to see where our denominator cannot be equal to 0. So add 2 to both sides and then take the square root of both sides, and we get x cannot be a positive or negative square root of 2. So it can be all real numbers except for positive, negative square root of 2, or we could give interval notation for that. So we start at negative infinity and go to negative square root of 2. We'll have to jump over the negative square root of 2 because I can't be equal to it, and then go to the positive square root of 2. Jump over that because I can't be equal to it, and then go on to infinity. And you could put union symbols in between those pieces as well.